So thank you for the introduction. So I'm going to present you the use case, our use case of HDF5, sorry, in geomagnetic data assimilation and visualization. Sorry about that. So I'm Loïc Huder. I'm coming from ESRF laboratory that is located just across the city. So the ESRF laboratory is a science lab. So we have all kinds of geophysicists working here. We have people studying chemical composition of rocks. We have people studying earthquakes, and then there is the team that I'm working on. It is called the geodynamo team, that is studying the magnetic field of planets and of the Earth in particular. And I'm going to give you a few concepts about the Earth's magnetic field to try to motivate the use of data assimilation and then the use of HDF5 for the output of this data assimilation algorithm. So, a few things about the Earth's magnetic field. So here is a slice of the Earth. There is a core here that we call the inner core, that is solid. There is another solid layer here that is the mantle. And in between, we have a liquid layer, in fact, that is called the outer core, that is mostly composed of liquid iron. And because there are heat exchange between the two cores here, there is convection, and then there are flows in this outer core, and because this iron is conductive, it is carrying electrical current, and then it is generating a magnetic field in a process that we call the geodynamo. So this is the source of the Earth's magnetic field. And this is in fact a really challenging problem, and if we want to study the magnetic field, how it evolved in time, if we want to try to forecast how it will evolve, then we need to know exactly how the flow will evolve, because this is the source of the Earth's magnetic field. And as I said, this is a very challenging problem, because it involves thermal coupling between the two cores, it involves fluid mechanics, because there are flows in the core, and also electromagnetism, because of the interplay between the flow, the current in the core and the magnetic field. And so people have been trying to tackle this problem for years now, using all kinds of tools. So numerical simulation and physical measurements. But this is, as I'm going to show, this is not perfect yet, because the numerical simulation are really hard to perform, because in the Earth we have a very fast rotating fluid with turbulence and, as I said, electromagnetism. So even state-of-the-art simulations, such as this one, where we have the magnetic field here with some turbulence and the core flow, are not able to reproduce all the features that we observe in the Earth's magnetic field. And so one may say, okay, then we just turn to physical measurement to try to measure it and know exactly how the core flow will evolve. But the problem is, as humans, we are living on the surface of the Earth here. So we only have access to the magnetic field at the surface and how it will evolve in time, if we do time use of measurement. But we have no way to measure the core flow and how it will evolve in time. And so that means that on one side, we have imperfect numerical simulation that cannot reproduce all the features of the Earth's magnetic field. And on the other hand, we have incomplete physical measurement. So the nice thing would be if we can try to use the best of two worlds, the best of numerical simulation, and integrate physical measurement into the simulation. And this is the aim of data assimilation algorithm. So this is a toy model, basic principle of sequential data assimilations that we use. So we have a quantity of interest here that we try to study. Its evolution in time. And to do this, we start at a certain point, and we will forecast this quantity using a numerical model that is, for example, the numerical simulation that I talked about. So these are the blue points. And then, at some point, because we know that these numerical simulations are imperfect, they will drift away from the real measurement that I've shown here in black. So at some point, we will correct this this forecast by assimilating the measurement data. And so we will correct the forecast with the observation at this time in what we call an analysis step. And then we'll continue forecasting, analyzing, forecasting, analysis, and so on. And this allows to have evolution of the quantity of interest that is more closer to the reality than what we would have only with numerical simulation. And so this is what we are doing in our group. And for that, we developed the pygeodyn package to do geomagnetic data assimilation. So the forecast is done with a reduced numerical model that is encoded to numerical simulation in collaboration with Julien Huder in Paris. And we are doing analysis to correct the output of this numerical model with up-to-date magnetic data that is measured with ground observatories all around the world, and satellite data, satellite measurements that satellites that are also orbiting all around here. And so this package has been in development for more than 1 year now, starting from Fortune code snippet. And one question that arose during the development of this package is what would be the output format, in fact. And so we thought a bit about this, and finally we turned to HDF5 with its Python interface H5 for a number of reasons that I'm going to expose now. And first, I would like to give you a few information about the output data that we have and what we need, in fact, to store in this HDF5 file and why we have chosen this file to do so. So, a bit of math. So, the magnetic field, we assume that it has this shape here. So, this is just regular decomposition in spherical harmonic. It is really classical when looking at harmonic potential in a spherical shape, in spherical coordinates. And in fact, what I want to show you here is that if we want to study the evolution in time of the magnetic field, we only need to consider these coefficients here that are shown in red, because these are the quantity of interest in our data assimilation algorithm. So these are the quantities that we are going to forecast and that we are going to analyze. And so this coefficient, in fact, that we call Gauss coefficient, correspond, as I said, to spherical harmonics that are just mode in a sphere. So we have several, we have different shape of mode depending on the degrees that we consider. And if you want to have the full decomposition, then we need to do the sum up to infinity. Obviously, because we are doing numerics, we cannot do so. So we need to truncate at a certain degree that I call big N. And this gives us, in fact, the number of coefficients that we will need to forecast and analyze. And in fact, this is given by n times n plus 2. And usually we truncate at n equal 14, meaning that to consider our magnetic field at a given time, we will have 224 coefficients at each time step. That means at each forecast and at each analysis. So this is, but the magnetic field, as I said, is linked to the core flow. So that means that this is not the only physical quantity that we need to consider. And in fact, at each time step, we have several vectors to consider. So we have, as I said, the evolution in time of the magnetic field that we call the secular variation, or SV, and this has also 224 coefficients. We have the magnetic field, obviously, again 224 coefficients. We have another term here that we call subgrid error because we are truncated at a certain degree. Okay, so there is an error that because we are not considering all the degree in our spherical harmonic decomposition. And so we have another term that is arising in this equation that has also 224 coefficients that we need to consider. And obviously, there is a core flow here that we call U, and that has 720 coefficients because the truncating degree is higher in this case. So again, I stress that for each time step, meaning each point in time being a forecast and an analysis, we need to consider all these coefficients. And in fact, this is exactly what I show here. So the outputs are reshaped for the forecast for each quantity. We have a number array of shape, number of time step, number of coefficient, and also because we are using a stochastic model, we need to do the data assimilation scheme several times to be able to evaluate the dispersion. And so this is what we call the model realization. So typically we have 20 realization, we have 100 forecast, so 1, 2, 3, and so on, 200. And then the number of coefficient is what I've shown in the previous slide. So that means that we have more or less, because we are storing in double precision, we have 10 megabytes, so it's megabytes. But this is only for the forecast. We also need to store the analysis. And so this is exactly the same, except that we don't have the number of forecasts here in the shape, but the number of analysis. And usually we have 2 forecasts for one analysis, meaning that the size is half the size of the forecast. So previously in our Python package, before the version 1.2, we were using a regular ASCII files. And so we had a file for each model realization, each step type, each quantity, which was not really efficient and led to really a lot of files. So around 200 for one of the earlier results of our Python package. And it was also difficult to manipulate. So this is the time where we said, okay, we need to find something else. And so I've looked a bit in file format, and I found this HDF5, looked nice. And then I said, okay, this is nice because now we can structure our data. And in fact, this is the structure that we have now. So here we have the file, and here we have in red what I call the group that are just H5 group. So we have one for the forecast, one for the analysis, and one for computed, which is something that we use for analyzing our result. And that is a combination of the forecast and the analysis. So maybe there's something better to do here. And for each group, then we have the quantity here that are the data sets that are directly the NumPy array, because in H5 you know that we have a one-to-one correspondence between the data sets and the NumPy array. And so now we have a single file that is really structured, and we are really able to access quite efficiently and in an ordered manner all the data sets that we have and all the quantity that we have. So to me, it's an improvement. And in fact, what I found really nice now with this file format is I can also add the configuration of my algorithm as an attribute. And this is really an added value that we did not have with the previous ASCII files. And so here I give an example of what configuration parameter we might have in our algorithm. So we have here the max degrees that I've talked about earlier that were called big N. So we have 18, we have 14 for the magnetic field, and so this can be changed by the user. We have the starting time, the ending time also can be changed by the user. And all these parameters, in fact, are stored directly as HDF5 attributes of our output file. And so we have these that are obviously stored as integer or floats, whatever. And in fact, these dates here are stored for now as strings. And the date array that corresponds to the array corresponds to the number of forecasts, for the date of forecast, for example, are stored as string arrays. And I think that's maybe that's not as efficient as it could be. So I would like to discuss a bit with you afterwards. And what's also one nice thing that I found about this is that once you have an output file with a given computation inside, then the parameter of this computation can be directly extracted from the output file to be reused. And you might say, why is it so important, in fact, to have this? Well, I find that when you have data sets here that are ordered, that are easily accessed, and that are in the same file as the parameter, then this gives you, in fact, an invariable tool for reproducible science. Because that means that at the same place, in the same file, you have your data sets and the parameters that are associated with it. And we saw in other presentations that people were really involved in trying to put all the experimental data, the energy of their beam and so on, with the data set to be able to know exactly what were the parameters of the experiment. And this is exactly, the same here. We are doing a computation, and if I look at the data of this computation, I want to be able to know exactly what were the parameters of this computation. And this is in fact something that can be used in conjunction with other tools, with other technical tools, such as semantic versioning and continuous release, so that you are able to really register all the changes that you are doing in your algorithm, and that every version number corresponds to a change in your algorithm, so that if you look at a computation that was done with a certain version, you know exactly what was the state of the algorithm at this version. And also with scientific testing, with continuous integration, so that you do not introduce any regression when you are improving your algorithm, in this case the data assimilation algorithm. So for short summary, so I presented you a bit about the motivation behind the geomagnetic data assimilation. I felt that it was quite necessary to motivate our use of HDF5 to structure the output data and to embed the computation parameter in the file, and that I found is a non-variable tool towards the reproducible science and research. So that was the main part of my talk. And now for a bit of relaxing, I will show some nice picture with HDF5 for geomagnetic data visualization. So this is the state that we are in. We have the pygeodyn Python package that gives us an output HDF5 file. And in fact, what we are doing also in our group is developing another Python package for geomagnetic data visualization that we call Webbased. And that is a web-based tool using a Tornado server, and that is deployed in a website that you can access and look at. It has the following web page. And in fact, what I wanted to say here is that this, the HDF5, through its interface H55, allows us to directly load the data sets and quite efficiently, and also have, again, all the parameters directly inside the Webbased server. And so we have a lot of visualization tools that are shown here. So I'm going to show you a few ones. So as you remember, we have Gauss coefficients that are forecast in time and corrected. And we can look at the time series of these Gauss coefficients to see how they evolve in time. And as you remember, these Gauss coefficients, they are used to reconstruct the magnetic field. And so we can display the magnetic field here as a color map on the surface of the core. And also the core flows that are shown here in streamline to see really the interplay between the magnetic field and the flow, and try to explore basically the result of our computation, how it evolves in time, and so on. So this was my partial summary, and I will just add that this HDF5 file format allows us to have an efficient interface for the visualization. And so show you here a few links that you can check out if you are interested. And I would like also to thank you for your attention.
Thank you very much. Are there any questions?
Thank you for your presentation. You changed a bit from the express sources. I guess you're storing mainly floating point data.
Yes.
Did you try the compression of the floating point data?
No. Sorry, you can continue.
No, it was really. Did you investigate the
as you can see from my previous slide, I said that for each data set we have 10 megabytes. So in the end, I have a file that if I store with double precision, I have a file that weighs 100, 200 megabytes. So it's, yeah, exactly. I didn't dig into compression option because I don't have the need to.
Thanks.
Any other questions?
If I understand right, are the files available for public download or only?
Yes, in fact, they are on the website that I show here. We have a tab that is that shows the download, and that is in fact we have the data sets for our previous publication there.
And one question. So, what are the Python packages you're using for visualization?
Here you mean? And here in fact it's web-based, so it's all done, let's say, it's homemade. So this is, in fact, this is the Python package WebGeodyn, and in fact it uses JavaScript libraries. So this is all in JavaScript. We use d3.js that supplies in fact all the visualization, except for the projection on the Earth, which is done in our group.
Any other questions? I have a question. What was the biggest change when you started with HDF5?
What was the biggest change?
Challenge.
Challenge. I don't know. No, really, I found, in fact, quite easy to set up. And as I said, because I was used to work with NumPy arrays, okay, I have a scientific background, so I use Python for scientific stuff, and so I was used to NumPy. And to have really this one-to-one correspondence, as I said, between the data sets and the NumPy arrays in H5, it really helped me a lot to understand how it was, how to manipulate them basically, and how to load them again as NumPy arrays as well. So really, for me, it was quite easy to set up. And maybe I need to ask my boss what he thinks about it.